Okay, so today I talk about Ricci flow with surgery. So we tell you something about how to do a surgery here. It will be a talk probably with a lot of description, but without giving a detailed proof. So let me say we already know so far we take giving a three manifold. If we take initial metric, and if this initial metric satisfies things, if say curvature of initial metric is bigger or equal to -1, or the volume of any unit ball is so let's put 0 here. It's bigger or equal to some. So omega is a standard volume in the Euclidean ball. So then we can say then there is a solution of Ricci flow. There's a GT. And the initial metric is G0, such that so this is exists on a t is between 0 and capital T. Okay, so such that first we have a curvature pinching condition. So phi C0 pinched. Okay, so that means if you look at the curvature tensor, this is bigger or equal to minus phi of R scalar curvature times R minus C0. So phi R is a function which goes to 0 as R goes to 0, okay, as R goes to infinity. And also let's keep a record here. We also know the minimum of scalar curvature is bigger or equal to 1/6/4t. T is the time. Okay, so this is one thing. Second, we know there's a kappa. Depends on all these things. Depends on initial value, such that this GT is kappa non-collapsed. And the third thing is we have this. So there is R0, okay, non-collapsed on the scale, on all scale. That's equal to RT, depends on some constant. Okay, so because yesterday, for example, some asked whether we can. What do we do if I have like a so-called bundle over torus? But here it's what about torus in the cause of deformation? But here we all these things we did so far is for finite time, including things here. Okay, so as t goes to infinity, capital T goes to infinity, this may be collapsed at infinity. Okay, so when we say non-collapsed, it always means it's within a finite time, because these scales depends on time here. So also there's R0. Okay, and the R0 may depend on these initial things too, but it's once you fix the initial, this is given. So this is also may depend on capital T here. So such that for any point xt, okay, if curvature, the scalar curvature of xt is bigger than the R0 of, okay, then we have following things. So then first we have an estimate. So this is called canonical neighborhood assumption. We have a so-called canonical neighborhood assumption. So that's basically follows from the following things. First, we have the derivative estimate. So that's equal to eta, some universal constant, depends on kappa. Okay, because this constant come out from a shrinking solidity things. So and RT, that's equal to eta R squared. So this is same as to C, and also the neighborhood is a neighborhood of xt is one of following types of epsilon. Is either epsilon lag or epsilon cap, or is a quotient by gamma. Okay. So in this last case, there's nothing we need to do, because so in this last case, we know the whole since this is compact and closed. So in the last case, if in the last case, let's just say it. In the last case, because it's closed, the whole manifold is just this, and then your flow will, because then the flow will shrink everything to a space form. So this case is once you are following this case, then you know after finite time it's everything is okay. Okay, so it's become a round sphere, So we can best exclude that case. So now let me say this condition here says. So let me define the following thing. To continue, let's define the following things. We define omega. They are following a paramount here. I define omega to be all x in the manifold. So let's assume t is maximum time. Okay, we can have a ordinary solution for this Ricci flow, and so we know the curvature will blow up as t. Maximum of curvature will blow up as t goes to capital T. So let's say take this to be assume a limit, upper limit of r xt as t goes to infinity. Goes to capital T is bounded. Let's consider this region. Okay, so first thing let me erase this and since I used that. So first thing I claim following thing. So I claim let's put it this way. Okay. So first thing I claim this is open set. So omega is open. Okay. It's open. It's easy to see why, because basically you can use this estimate here. So this so first we know if there is a sequence, so you can check if a limit of x, so see this, if a limit x ti goes to infinity, so that namely this inverse of x ti, x is fixed, it goes to 0. So then as goes to infinity, of course, after a while you can assume this is satisfied. So then you have this estimate here. Okay. So then you can have so then for this ti you can have at least for nearby this is this inverse of t will be bounded. Okay. Now since ti all converge to some finite number here, that will imply this will imply this goes to 0 identically, uniformly so that means r x t I t is goes to infinity. Okay. So I guess I probably don't need to do this. As t goes to capital T. Okay. So you get here. So on the other way, so I know this is so this will be uniformly. So once I know and it's bounded, then how do I say? Maybe it's okay. So now this say we can have this uniformly bounded. So okay. So same argument. Maybe I don't read. Okay. Actually, but anyway, so this is this roughly see why this is a case. So that that's imply same. This argument here says the following. So says if t, so same arguments imply moreover is if t minus t is so what I want to say is a following. So suppose I have this. Okay. So suppose I have this. So maybe I erase this. So this is the same argument. So maybe I do this way. So suppose Q is say Q is a supreme of T for supreme of R x T for T between capital T minus some delta and T. Okay. So delta is very small. So then this is finite. Okay. So then by this condition we know this is so by this condition here we know there is delta prime such that maybe it's at order of we can even figure out, I guess, this delta prime. Okay, such that this stays bounded. Scalar curvature of x at the t minus delta. Okay, and prime is less equal to a q for so less equal to say q plus maybe twice of eta. Okay, for any x prime inside of this ball of at t minus delta and delta prime. Okay, delta prime. Okay. So maybe I put r prime here. Sorry. Okay. So then if this delta is sufficiently small, you can use this to prove. So then you can also do so using this second identity, using this since eta since r t less equal to eta r square. Use this, you can prove this r x prime and the t is all maybe bigger than less equal to some constant. Okay, so maybe I put some constant, maybe twice of this plus some big constant for when the delta is small. So in this ball. Prime cross t minus delta t uniform. So here I assume delta prime, delta small. so this is basically previous what I did. I erased. It's if it's not too big, then the inverse of this will have something very small, and on the other hand, you know at least a certain point the inverse this is bounded from below by some positive constant. Okay. But anyway, so this is trivial to. Okay. So this is open. So the complement is a complement for any x in m minus omega, and we know this is the limit Rx we just proved is equal to infinity. T goes to capital T. Okay, capital T. And we know the following things for any, and moreover, so for T sufficiently close to capital T, so there is a neighborhood. So such x T has a neighborhood which is of following type. Is of which is the same as epsilon lag or epsilon cap. Okay, epsilon cap. Okay. Or could be this too. So, okay, I mean, if omega is empty. Okay. So this case is so each of so near, so for point here, okay. So here I have to remind you the point for any point here, for such a point. So now we can divide into two things. So one is say if so omega is 0, is empty, then everything falls into every point has such a property. So then what you get is you might get then the manifold is of a following type. Okay, so then the manifold is of following type. One is a possibility is of course S3 quotient by gamma. Okay, and the other possibility is you every point is given by epsilon lag. So but it's closed and manifold is closed, but every point is covered by epsilon lag. So this is like S2 cross S1. Okay, so this case is like maybe I draw a picture here. Is so your manifold is so this cross section is S2. Cross section is S2. So your manifold is every point is covered by epsilon lag going on. Okay, so this corresponding to this case. So you can also have somewhere is covered by epsilon cap. Okay, and epsilon cap. But epsilon cap has two kinds of epsilon cap. So one is so both the epsilon cap here. So here is epsilon cap. Okay, but epsilon cap has two types. One is just like S3. Sorry, it's S3 minus a ball. Okay, minus a ball, or topologically, or is RP3 minus a ball. Minus ball. Okay. So for example, this can arrive as one of these shrinking Soliton things. It's like S2 cross R quotient by Z2 here. Okay. So then if I have this case, so I have a different combination of this. If I have two of both epsilon caps are given by this, then I just get S3. Right? So if one of them is given by this and one of them by that, so I just get RP3. Or I can just get RP3 connects on with RP3. Okay, so that's a topological types you get. Okay. So I guess I can drop this into a previous case. So I restate, repeated this again. I can throw this to a previous case. So anyway, so I have these cases. Okay. So if at capital T, no bounded curvature, curvature is blow up at every point. So this is a case when in particular the Ricci flow, the GT become extinct. At capital T. Okay. So then you know this manifold. So then the manifold is just one of these types here. Okay. So for example, if you assume a manifold you start with simply connected, then only thing you can get is this. Only thing you can get is this. So that's Poincaré conjecture. Okay. That's Poincaré conjecture. So end of this course, I want to prove this has to be 0 at a certain point. Okay. So now if this is not 0, so what do we do? So if it's not empty, the first thing we can do is so we know the curvature, this is open, so curvature is always bounded near here. So by derivative estimate, derivative estimates, the curvature of this is bounded uniformly. Not only that, the derivative of this are uniformly bounded by some constant ck, and also depends on distance. This constant also depends on, maybe I say uniformly bounded near any points. Near any points near any points inside omega. Okay, for any k. Of course, this bound may depend on k. Okay. So by why is that? Because we know the curvature are uniformly bounded nearby omega. Then we can apply a derivative estimate to get all high order derivatives. Okay. So then since all the derivatives are bounded, so flow converge. So imply the GT converge to some metric. Maybe I use the notation here. So let's just write this as a capital T. Okay. So maybe I write as a capital T. Okay. As at point maybe xt going to converge to some metric as t goes to capital T. Okay. So we have a smooth metric. We have a smooth metric on omega. So now I want to use this smooth metric only defined in an open set. I want to continue this metric by carrying out certain surgery process. Okay, so to do that, what I said is I make some let rho, okay, set let. Okay, so the rho be less equal to R0 there. In fact, we want it to be less equal to R0, be some small number. So usually it's less equal to so-called delta R0 for some small delta. Okay. So I want such. So I pause this. Then I define a set omega rho such that this is all the points in the x in the omega, such that the curvature is the curvature of G capital T, scalar curvature capital T of at x is bounded by rho of. So this is a subset of omega. You can easily check by again by this derivative, by this canonical level assumptions, and the derivative estimate. You know this is omega rho. In fact, omega rho is compact. It's compact. Okay, you just so it's a compact set. It's closed compact set. Okay. So since the rho is so small, we know. Moreover, we know for any x inside of omega, outside omega rho. So that's why I chose rho is so small. Okay. So and in fact, so far I only use the assumption the rho is less than R0, less than this scale where you have a canonical neighborhood assumption. So for any of these, we know since omega rho is let me pause this way, sorry. Okay, so okay, because so then this one is every this is there's a neighborhood which is either epsilon cap or epsilon lat. Okay, that's because this is ruled out. Yeah. So here I assume omega is non-empty now. Otherwise, you might have this. Okay. So I have this. So now let me draw the picture instead of. So okay. So here is the thing. So my space is basically like then we analyze. Okay. So there's three manifold. So I have to draw enough cases so I can illustrate. Okay. So this so I need to draw more. Okay. So there might be also the case and the case of the picture of like this, and then okay. So let me see the blue part is see this is so this is a part where you have is omega rho. Okay. So omega rho. See? So omega, I guess this blue is very hard to see. Rho. Okay. This is omega rho, and this is omega rho. Okay. So outside of this this omega rho, and in omega, and here the points are missing. Here is which is already outside omega. Okay, but the blue part is region is omega rho part. Okay, so outside omega rho, but still in the omega, maybe. So I have each of these at each point, is covered by some epsilon lag, or by some epsilon cap. So what we can do here? So we can do so starting from any point here. So we start from any point, say x, on the boundary of omega rho. So we can continue to so in fact this is not possible. So this is okay. So at each point, let's see. So we basically have 5 cases outside this. Later case we can take. Okay. So okay, so this is also possible. I'm sorry. So it's a cap. So what we do is here. Okay, so for each point here we start. So this point, since rho is so small, this rho is so maybe I should push forward. Let's push a little bit further because rho is so much smaller. So I look at the point x here. So this is contained has a neighborhood which is epsilon lag or epsilon cap. If with epsilon lag, next we can extend this point to here, and this point is outside rho. Again, you can cover it by epsilon lag. So you can continue this until you get cap. You cannot do it. Otherwise, you will get home. Okay. So for example, like here, you can continue to get home because you continue. You always get epsilon lag all the way. Okay. And so here you get epsilon home. Okay. So here you also get epsilon home, and but here you get epsilon lag all the time, but then you touch to another boundary component of omega rho. Okay. So what I try to say here is you start from any point on the boundary component because it contains the epsilon lag or epsilon cap. If it's epsilon cap, you stop. If not epsilon cap, if it's epsilon lag, you continue this process. Push for out. Okay, so until you cannot do it. There's few possibilities. One is you arrive in an epsilon cap, then you stop, or you get to another boundary component, you stop. Okay, so you otherwise you extend all the way, you get epsilon home. Okay, so this way, what we get in the end, we get 5 cases outside. So this way we get we conclude the following thing. So by this, so each, so let's put it this way. So each epsilon lag, okay, of omega is contained. So it's contained in a one of the following subsets. So A, this is called epsilon tube. The epsilon tube is just made of a union of epsilon lags. A epsilon tube with boundary in omega rho. Okay, so it's okay, so it's like this case. Okay, it's this case. Okay, so it has to end up somewhere. Okay, so okay, second is epsilon cap with boundary in omega rho. So like this case. Okay, and thirdly, like epsilon home, like this and this case. Home with boundary again in omega rho. So I have 3 cases. So other case we can have is the capped epsilon home. So it's like this here. So it does not touch omega rho. It does not touch it. So it's a home on this end, but it's a cap on other side. Okay. So it's disjoint from omega rho in the limiting process. So last case is a doubled. So it's like here. So you might have several of these epsilon homes. You might have several epsilon homes, and you have no control on number of them, a priori. Okay? So you might have several ones before you reach a piece. So you have these cases, and all those cases, okay, what we do is all these cases are then the volume of this piece, and the volume of this part, this subset, in one of these subsets. So okay, the volume of this subset involved, like outside, is always big equal to some constant. This constant may be very small, and the rho cube. Okay, because you can simply look at can at least contain little ball here, which has that size. That size. So volume of this part, because this part I need to cut off again, we always have a unit size. Have some definite size. But these ones here, and this one here have no control of volume. Could be very, very small, teeny, very, very teeny. Okay, and it could be like here. It's very, very, very small one. So we have no control of volume on this case. So now also topologically what we do is and this is double epsilon home, so it's basically S2 cross R. Okay, and the epsilon cap case, there are 2 cases. One is S3 minus the ball. You take out the ball because the ends is the cross section is already S2. Okay, always S2. So this is like could be S3 minus a ball, or could be RP3 minus a ball, because you might have a S2 minus R quotient by Z2. This is like RP3 minus ball. Okay, so this cap case could either be a ball all be a RP3 minus ball, and same as here, and so on. So what you do here is, and these things I will throw, so this I will throw out, and this I will throw out. So what you throw out is topological simple things. So let me conclude this. So okay, so I know the manifold is obtained this way. So from here we get M. Okay, so M is diffeomorphic to a connect sum to connect sum of connect sum of omega j bar. Okay, and with a finite many S of S2 cross S1 and RP3. Okay. So where omega j are the components of omega which contain these contain omega rho, some points in. Omega rho. Okay. So basically, for example, what we did here is so look at the component. For example, this is one component. Okay, so this is one component, and this is here my job to have two components, omega rho. Okay, two components, and I'm sorry, I have three components. This is okay. I have two components. I'm sorry. Okay, two components because this is a component for omega which contain the point omega rho. So then these things throughout, I just it doesn't matter. It's just S to cross. I can forget topological. I can forget about this. I just directly glue them. Will not change the topological type. Okay, and here, if this is RP3 minus a ball, then I keep it. Otherwise, it's just the ball. Topological doesn't change by throwing that. Okay. So that's. You get this. Okay. So in the following, when I do a surgery, I cut off something from this omega, but I will first throw out those components which has nothing. We throw out those components which do not contain any point omega rho. Okay. Omega rho. And the number of you have no control on the number of components throw away. So now I do a surgery. so when we do a surgery, we only do a surgery along those epsilon epsilon homes, which okay. So okay. So now let me so in this same picture, what we do is we will through this and through this. Okay, so okay, and now after throwing some components out, of course, become disconnected. What I want to do next, I want to cut these things at certain point and replace by some standard solution and continue the flow. So for each epsilon home, for those I don't care. Okay, for each epsilon home, I will do some surgery and close them up and try to continue the flow. Okay, so here, in order to do a surgery, we need some lemma here, which is okay, it's a rather technical lemma, which it's actually not harder to visualize. So there is H, the size which is less than a positive H, less than b 0, and less is equal to rho of, again, rho delta is very small. So forget why I write this way, because basically it's I guess we follow the paramount and so on. It's kind of convenient for later purpose, but it's hard to explain here. So anyway, so delta is very small, so I want H to be much smaller than a rho again. Okay, so and delta is much smaller than epsilon. So epsilon is rather fixed at the beginning. Okay, so epsilon is small but fixed now. So delta is much smaller. Delta will be much smaller than epsilon. So we need this. So depending on of course, depending only on the delta or rho or these pinching things. Okay, so such that for every x, okay, for any okay, for any x in the omega this, okay, with maybe in a let me state it in the with sorry, each x with hx, which defined to be a curvature of x at capital T. Okay, that means a curvature of gt. So maybe I put it this way: g capital T of minus half is less equal to h. So in a epsilon home of omega rho. I'm sorry. Epsilon home of omega g of t, with which has boundary in omega rho. Okay, like there is the neighborhood you take a p of x I will define this probably T x delta inverse H x. So this is defined to be a ball of x capital T and the delta inverse of H x radius, okay, cross with this capital T minus H square, capital T. So it's a strong delta leg. So namely, so namely, there's a diffeomorphism. So there's a diffeomorphism of a phi from this P here, okay, into this S2 cross minus delta inverse. And maybe I do it this way, okay, such that this phi, you pull back the metric GT. So then you scale to a H minus square x. Okay. So you compare with the standard metric here. So standard metric here. Okay. So I should say the flow here, up to capital T. So flow here, up to capital T. So again, so this is H square of a T. Okay. And the cross on the cross capital T. Sorry. So minus capital T. Okay. I'm sorry. Okay. So this is close to a delta close to a standard metric. So that's a product metric on the. So this is like a 1 minus the standard metric. Maybe product metric in a C. Topology. Okay. So T is from this time from -1 to 0. Okay. T is so here T in this way. The T is this T is here is maybe I put S here. So S is from -1 to 0. I can even close up. 2. So I have these strong things. I'm sorry. In fact, it goes from 0 again. Okay. So the flow on this part is very close to this. So this is a little improvement of because previously I only assume it's the epsilon lag. So namely the size of in the original scale is only like after scaling this curvature is from 1 epsilon inverse to this, and only epsilon lag is epsilon close. Okay. So now I want this. If you go deeper into a home, so I want this to be getting closer and closer to a standard solution. So it's delta close. Delta is much smaller than epsilon. Okay. So this is this thing. So namely, if you go continue into a singularity, and you are getting closer to a product metric. So that's a thing. So how do we prove that? It's actually prove is batch contradiction again, because if you, for some delta small you don't have this, you can find a sequence of. If it's not true, you can find a sequence which are always local to epsilon, has an epsilon neighborhood, but for any delta, it's not close. It's not there close to delta lag. So then you take a limit. Okay, you scale. You take a limit. So in a limit, you will get some ancient solutions. But this ancient solution has to be a product. Why? Because you go deeper into this direction. So and the home has you have an infinite distance to go into that. I mean, not infinite. At least they have infinite many lengths after scanning to go there. Okay, after scanning you have infinite lengths, and because it touches this omega rho, so you also have a long distance to a fixed component. So in the limit, it should have a straight line. So then it splits. Okay, so it's ideal is basically you know this home is touches that. That's if it's not true, you will get something with a splitting line. Okay. For other homes, you may not have this property because you might you in the limit it may not split. Okay. So I used this fact. This home also touches some fixed part here. So once I have this, you can. So now, what I want to do here is I just look at one component now. Maybe I enlarge it a little bit. Okay. So I look at the epsilon. Look at one section. This is delta lag. Okay. So and this is the middle cross section of delta lag. Then I want to replace this by some standard solution here. Cut this off and get standard solution. And then continue the flow. Okay. So now let me state the property what the standard solution is. So I just state okay. So let me see. So first we claim following. So next I talk about some standard solution. It's very simple here, so I just state some. The first thing I know, I collect a few facts. The first thing I know, there's a standard initial metric. There's I call the standard initial metric. On S2 cross on R3. Okay. So let's call the G0, satisfying the following things. Okay. So of course it's complete. So let's see. So let me put it this way. So first is complete. Okay. And the curvature is non-negative. Okay. That's easy to do. So invariant and SO3 actions. Okay. It's a rotational invariant, so it only depends on one radial directions. So also I want to say there is a ball ball contain R3 such that the metric G0 restrict to R3 minus the ball is isometric to a product metric. So metric on S2 minus the interval. Okay, so last thing I want this to be, and it's easy. So last thing I want to say G0, and the curvature of this is constant, equal to say 1/4 the center of a ball. So this is just for convenience when you do surgery, because I didn't erase this here. Erase that. So anyway, I want to keep that curvature pinching condition when I do a surgery. So that's why I need certain curvature conditions. So then you run the flow. Okay. So then what you do is okay. So then you can run the flow. So this needs to be proved. And first, then there is a solution. Okay, so there is a so-called standard solution. The solution GT on R3 cross 0T with G0 equal to G this, okay, such that again first uniqueness okay. So namely, if you start with two solutions from the same initial data, they will be the same. Okay, so this says so if R3 and G prime is another solution, then the G prime equal to G. Okay. And this is needed when you want to establish those canonical neighborhood assumptions for flow with surgeries. Okay. So far, all the discussions I assume the regular Ricci flow and examine structure near the singularities. But then after this, after doing a surgery, I want to repeat all these things. Repeat what I did for regular Ricci flows. So in that case, you need the actual property from a surgery process. So I need this uniqueness, and this is actually Perelman suggests the simpler. I guess he suggests the proof try to not using a PDE method. And it turns out it was not right. So you still need to use the PDE method. And the whole point, because Ricci flow is not elliptic, as Luis probably already talked about that in proving a localization, proving a local existence. So you cannot directly prove uniqueness for non-parabolic equation. So what you do here is you need to first reduce the problem so-called Ricci-de-Tocque flow. You need to make a flow to be parabolic. So for that, you need to solve certain harmonic map flow equations. But that's harmonic map flow equation on a non-compact manifold. So you need to do something. It's not it's kind of expected. Okay, so we found some way of doing that without using any deep results. We just try to reduce the Euclidean space case. Okay, we reduce R5, some flow equation on R5. So anyway, so you have uniqueness, and the second thing is T actually is 1. Maximum solving is 1. So you need a certain length to go out, and the curvature is positive. So for t positive is strictly positive. Okay, and it's invariant. Okay, so and also it's this is it's invariant and non-collapsed. Okay. So let me just state. So and asymptotic to a cylinder. To a cylinder. To symmetrical solutions. So that means this standard solution on these things after proper scaling. After proper scaling. Okay. So once you have this, what you do is you can do a surgery with the following situation. So let me enlarge things. So now let me enlarge one of these pieces here. So for surgery. So pick up the epsilon lag, a delta lag. Okay, from this omega touches omega rho. So let's fix this. So let's say the rho is a map from S2 minus delta inverse into pick up leg set, let's see, n. Okay, so n is here with a center at x0. Okay. So then we look at standard solution R3. So what you can do is maybe I just draw the picture. So we can map this, say this to be like 0 of some point here. So some point here at like P in this map goes to x0, which is the center of in the central section, cross section of. Okay. So now we define so I just give you a precise definition. Then I leave you to check. All computation are rather trivial. So I define this function S, okay, to be a projection pi 2 composed with rho inverse. Okay. So basically I give some radial functions on the n. Okay. So also by this choice here, we know there is isometry. Secondly, and do I need to do that? So what I do is maybe I draw quickly. Okay. So now I have let me draw the picture. So I have this n here. I enlarge. Okay, after scaling to unit size. So this is n, and I have a sphere here, x0, which corresponds to s equal to 0, and this is goes to s go to minus infinity. Okay. So this is slightly perturbation of a cylinder with a curvature, scalar curvature equal to 1, scalar curvature equal to 1. Okay, so this is S2 cross or minus delta inverse. So this is just a slight perturbation of that, and the deviation is within the deviation is within delta. That's why it says delta close to that. Okay? So I just draw the picture to see. So then I know this is I can close up here in a sense. So this is a negative part S. So I can have for my standard solution. I look at on the other hand, I look at the standard solution. I have a very large things. So then I have this. Okay. So basically that thing over here is you have a cylinder, then covered by some semispheres. But the semisphere is not smooth here, so you're smoothing a little bit here to have that things. So that at least I know this is outside the compact region. Outside the compact region, say this is B. Okay, the whole thing is R3. Outside the compact region is just a product. So outside compact region is a product. So I can say so I can assume this is I can match this with this. So this say I have this is equal to S equal to 0 here. So then say this is S equal to 4, just for convenience. You can take any fixed number here. So this is a cylinder. I can identify with this outside this. So say C. So this is a B, compact set. So outside compact set, by construction, I can assume this is just a direct product. So this part can be identified with that part. So then we do we set up we have a metric here, which is the metric here is given by this side is given by R x0 of G of T. Okay, this side given by this, and it's pull back to here. So then on here I will have a pull back of GT times R. So here I have a standard metric. Maybe I call the standard metric is so on this part is I have a G0. Okay. So through a row, I will pull this metric back to here. Okay, back to here, and then and then I have G0 here. G0 here is this is a cylinder. So G0 on this part is just is different from that metric with by delta. Okay. So I guess let me write here. So now we define define F as to be a 0 of okay. So it's a 0, S less equal to 0, and C0 exponential delta exponential. Okay. So here the C0 and Q are only constant, and the C0 is not Q. This will be chosen in order to fill in that pinching condition I will declare later. And both independent of these are independent of delta. Okay. So then what I define a metric G roof G hat to be a exponential minus 2f s and r x0, okay, and pull back this gt. So basically, I pull back this metric back to here. Then I try to cut off gluing with this standard one. So this next is exponential to f. Okay, so this is for on a S inverse of minus infinity to 0. Okay, and so then this is alpha s of r x0 of rho star of gt. Let's just put g here. 1 minus alpha s of eta g0. Okay. I tell you what eta is. So this is on S. This to 1. This is to. Okay. So then exponential of minus 2f. This f is needed in order to tame the curvature conditions. You want to. This was already used by. So this is in the Hamilton in this for 4 manifolds with isotropic positive curvature. So this is on S inverse to some of these some of this region here. Maybe I put AR0. Okay. Okay. So then so because you want to do this, f is used for pinching, but in the end, you also want to drop f to get back to a standard metric. So this is so then this is a beta s of exponential of 2 plus 1 minus beta of exponential of some fixed value at 4 times A0. A0 is some big number here. Okay, and eta G0. So the rest. Okay. So where the so this B, so B is a ball from B from this tip, the vertex point to A0. That's A0 is radius of that. So this is A0. So we need A0 to be big, so that is okay. So A0 is some big constant. So we have this, and where maybe AR0 equal to 4 times. Okay. So yeah, eventually your metric, new metric is just G prime. You back to a scaling. So Rx0 inverse of. So that's your metric after surgery. So this is you normalize. Okay. So what is alpha beta here? Alpha beta is simply a cutoff function. So alpha will be because you want alpha to match this metric matches these metrics here near the 1. So alpha is 1 near the 1, and the 0 near the 2. Okay. So here is same thing. So you want this to be near this 2 is 1, and near R0 is 0. So remember, this is a constant. It's a constant. Okay. So after doing this, so what I will get is I will get each of these is I closed up with this, and this will keep originally. So this, and so become a two component. So now I continue the flow. Continue to flow with this as the initial value. With G, T, so to continue the flow with this as initial value at capital T. So you pass the capital T. So we will need two things to make sure to this is work. So one thing is so you have a couple of properties you can establish. Okay? So properties. Okay. The first you need the curvature to be pinched. So namely, you need Rn after surgery, you still keep these conditions for G tilde. And you also want the minimum less bigger equal to T. Okay. So of course, this is only you need to check this property near the part metric is changed, because so let's see, I have this is 4 here, so this is s equal to 1 here. Of course, before the s equal to 1 is just original metric. Certainly, these conditions are satisfied. So only thing you need to check is to choose this choose these constants appropriately, so that this property will be still satisfied on this part, okay, on this part. Of course, near here is okay because curvature is even positive. So basically, your check is that on this gluing part, Okay, that's why you need this F is a little bit in a different way. So also, you can make it. So this is property was never stated in the paper, only when he needed he brought that up, say there's such a property, but this can be seen is since so I didn't put eta is 1 minus delta. Okay, so namely, since this original metric is within a delta distance from a standard metric, so now I shrink this by delta, by delta here. It's different data from canonical neighborhood assumption. So this thing maybe I put a bar to distinguish. Okay. So then this metric is always less equal to this metric here. Okay. So choice of eta bar tells you this metric Rx0 after scaling of this GT of fallback. Then you can compare. It's always big equal to eta bar of G0. Because this one is delta close to a standard one. And you shrink that. So this probably tells you, so clearly, original you have this cone over here, which I erased already. And you can crush this home to this point, and you can And here is just standard map. So namely, there is a map from original manifold to this one. It's not isometry. There's a map from original manifold to of omega, maybe omega bar, and that is closer to your new manifold after surgery. So let's say M after surgery. Okay. So maybe I put a T here. So capital T. Okay, this is new manifold now, and this is and this with and such which is such that phi is identity is just identity outside. Let's say S. So for when the value of S is less equal to 0, and phi is distant decreasing. These are two things that are easy to check because basically you can check that when you do a surgery. Okay, it's explicit and thing. The harder thing to check is so now you want to continue the flow. You want to see a lex. You still want to have a canonical neighborhood assumptions. Okay, so now so next I want canonical neighborhood assumptions. Of course, when I say this, I need for Ricci flow with surgery. After surgery. Okay. And this is the harder thing to check. So namely, I need to check surgery will not affect all these arguments I used before. And I think my time is up. So maybe I just state things. So maybe I say I don't know if I have time to say this. So because I didn't have time to define Ricci flow surgery yet, which actually I defined at the very beginning. So let me just state it now. So this is surgery process, and so in the end, what you can do after many work, mainly is because this is most difficult part. This is basically in the section 5 of the things of this Paramount second paper. Also in the in the chapters of our book, it takes quite a few pages to do that. But in the end, what we have, so we can have okay, so in the end we want to get things. So I want to say there is a sequence of okay. So I don't know what the so I guess I state the theory. Okay. So there are two functions. Okay. So there are two functions, RT and the delta bar T. Okay. So decreasing function, and the Ricci flow with surgery. So let's see, m of gt, mtgt. With the normalized initial data, with given initial data. Which I already stated at the beginning, such that so this is on a 0 over infinity, such that mt gt for mt prime t prime satisfies this canonical level assumption. With the parameter. So namely, there's in an assumption so epsilon is fixed. Okay, the parameter is there's a radius there with radius r t for such as for t prime less equal to 0 t. Okay, that's and curvature pinching conditions. Curvature, okay. And what is the delta bar here? Okay, so furthermore, so this is yes for each t, and so thirdly, so there are only finite many. Okay, and there are t0. Okay, such that mt is the same as mti for t less different of ti plus 1. Okay, let's make this to be t0, convenient, and mti plus 1 is the obtained from mti by surgery. As we said before, with the parameter with h given by this. Okay, with the parameter delta bar. So that means so to coincide with the so I need h to be less equal to a delta bar of rho, and rho to be a delta bar of RT here. So with RT here. So that's the answer. And so let me stop here now. So I will say, maybe I should say why and this is a no accumulation point in the finite time. Why is that? Because I said each time I do a surgery at finite time, it depends on rho. Okay, you take out a certain volume depends on rho. At least depends on h here. Okay, h is rho. So then it's finite because so they somehow built in this proof too. I have these uniform things. For any finite time, it has a no bound, positive no bound. Okay. So because this delta, you remember in this, if you go back to check this, think more about this proof we had, is we can make this to be uniform away from 0 if at any finite time. So of course here you need to worry about the surgeries. As long as no surgeries, this one previous we choose R0 and the delta, they can be made uniform at any finite time. Okay. So since here we can also make in proving this, it's very technical, this part proof. It's like proof by contradictions, but they are like they're running out several contradiction arguments at the same time. So it's impossible for me to do it here. So anyway, I'm probably not the best to do that here. So not because for presentation, I certainly understand the proof. So in proving this, you just best say this surgery will not affect the previous arguments. So previous argument, there are two things. One is kappa lung collapse. So once you have kappa lung collapse, and then you say, okay, this end of last course, I very sketch way I talk about this proving the complex argument. It turns out that argument can be extended here. By using a properly standard solution, you can avoid the blow up part. So when you come to this, if that thing does not hold, actually it's away from the surgery part. So you need to make sure that. So once you have that, then you can, if you think more about what we said before, and this can be made uniform at any finite time. In terms, that it will imply no accumulation point, because each time you do a surgery, take away from certain warnings, depending on role. Okay. So there are only finite surgery at each finite time. But you cannot guarantee, you might have infinite many surgeries, and you might do a surgery more often as t goes to infinity. Okay. So one more thing is all these things I emphasize, I did so far is at finite time. That assures I only need to do a surgery along S2. As t goes to infinity, I don't have that luxury. So I have to deal, for example, the tori, cutting along the tori. Okay, I stop here. So next time I try to finish a proof of Poincaré conjecture by proof even for this generalized solution to Ricci flow, it has to become extinct at finite time. If a manifold is simply connected.